All right. Uh, Class ended so fast that I think there was a lot of questions, and so I just wanted to take a quick minute and explain um, the last couple of things. That we did right at the end. So one of the more confusing pieces was trying to find the 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 speed, right? So one of the questions asks for the average speed. So the average speed at 5 was just simply take your 6.25 and divide by 5 seconds because it goes 6.25 meters in 5 seconds. So that would give you the average speed for the first 5 seconds because you're looking at the first 5 seconds holistically. The next question says, what is the instantaneous speed? And so basically what you want to do is just look at how far did it go per second, right around 5 seconds. So for example, if we look at just these two, we see that it went from 4 meters to 6.25 meters, and that took 1 second. So its speed would be about 2.25 meters per second because it's going about, right, it went from 4 to 2.25 or to 6.25. That's 2.25 meters in 1 second. So that's how you find the average or the instantaneous speed right at 5 seconds. So then it says that you need to make a position or a velocity versus time graph, which means you kind of need to know the instantaneous velocity for every second. So like, let's take a look at the beginning, right? The beginning, we know it's going slowly. We know it's going slowly for a couple different reasons. Let's get that graph out of here and this graph out of here. All right, we're going, come on, right? So we know that this object is speeding up. The reason that we know that is because of the slope of this graph right here, right? The slope of this graph, this is a position versus time graph. It says distance, but probably position is a better way to look at it. But a position versus time graph, and um, right, the slope of this graph is going to tell you the speed. So if we look at the slope is very flat at the beginning, so it's not going very fast. And then as time goes on, it gets steeper and steeper and steeper, telling us it's going faster and faster and faster. So this is kind of confirmed by actually looking at the data. In the first 1 second, it only goes 0.25 meters per second. So its velocity for the first 1 second would be about 0.25 um, meters per second. So that would be its speed. And the way I got that is just, it would be like the distance that it traveled divided by the amount of time. So it traveled 0.25 meters in 1 second. So in theory, if we look at the equation I just did, B3, which would be this one, minus that one would give me the speed. And in theory, it really should be divided by 1 second or divided by the one um, should be divided by the difference in time, but the difference in time is always 1 second. So like if we look at what I did, I just took the change in distance divided by the change in time. The change in time is always 1 second. So it's just boils down to be basically, you know, 0.25 meters per second. However, we look at the very end, right, it's going to be 36 minus 30.25, so 5.75 divided by 1 second because it took 1 second to go from, right, from 11 seconds to 12 seconds. So that's how we got all this data. You can do it, you can do it automatically, or you can just put in a little equation to have it do that, and then pull that equation down and apply that equation to every other part, to all the other cells. Then you just need to make a graph of your speed and your time. Oh shoot. So keep in mind that we got to have our cells match. So you want to, if you do, right, only those ones, then you also only want to do that one. So when you go to make the graph, just make sure that you're not unevenly matching your cells. So what that would mean is, just to show you what that looks like over here, note that it says it goes from A3 to A14 and D3 to D14. So just make sure that, right, that they both start with the row 3 or whatever row it corresponds to on yours. So, but you shouldn't have this be like A3 and this be A2 or D2. Like you don't want them split, if that makes sense. So just be careful of that. Okay, so this is our velocity versus time graph. So that's what that looks like. I'm gonna jump over and do a couple of things on paper for you, and then we'll come back and conclude some of the answers here. Okay, so all right, for part 2 of this, I want to talk about what each of these graphs mean. So you have 3 graphs that we've gotten so far. We have our first graph, which was an position versus time graph, and that was, right, a top opening parabola. Then we linearize that graph, and we have a time or a position versus time squared graph, and we got a linear line for that. And right, following the y is equal to mx plus b equation, that's going to become x is equal to, the slope that we found was 0.25, so 0.25. Right, we have time squared on the x-axis, and there was no y-intercept, so that would be the equation that we got for that one. Okay, then we made a velocity versus time graph, also linear, following the y equals mx plus b equation, we are going to get velocity is equal to. And if you look at the slope of this one, you should get somewhere around 0.5. So we have 0.5 t for our equation. Again, the y-intercept should be fairly little. So this is the 3 graphs that we have. It asks you to analyze the sloped units. So if we take a moment to do that, we should see, right, that the right slope is rise. So this is on the, for the rise, we have meters because it is position on the vertical axis over run. And on the run, we have time squared, which would be seconds squared. So my slope is going to be equal to meters per second squared. Okay, so those are going to be my units of the slope. Here, the rise is going to be meters per second because it's velocity, and the velocity has units of meters per second, over run, which is seconds. So the slope is going to have units of meters per second per second. Okay, so let's pause for a second and see if we can gain some of the meanings. You'll notice that in class I skipped over what is the meaning of this. And so we have, but this one's a bit easier to figure out. So we'll come back, but let's look at this, right? Slope is basically your change. If you think about what this is going to be, this is how much your velocity is increased or changed, because you could have a negative slope, right? So how much your velocity has changed over how long that is taken. So this would be your change in velocity. And this would over your change in time. Right? How long it took you to change that velocity. So if we think about changing your velocity, that would be speeding up, that would be slowing down. We call that acceleration, right? So the meaning of the slope here is acceleration. Okay? Now, real quick, let's take a closer look at these units. Let's see if we can simplify these units. Okay, so we know that the slope, the meaning of the slope for this graph is your acceleration. How much are you speeding up or slowing down? Okay, and let's take a look at this and see if we can simplify this. Let's remember that dividing by a number is the same as multiplying by the reciprocal. So if we look at what this could happen, right, this is turn into, dividing by an s is the same as multiplying by 1 over s. We look at that, meters times by 1 is going to give you meters, seconds times by seconds are going to give you seconds squared, and look at this, the units are the same. So why is right? So that means that the slope here must be related to the slope here. They have the same units, and so they have to be somehow related. Okay, so let's take a closer look at the values now, right? So we have 0.5, which is our acceleration, and we have 0.25. So if this is a, then this must be 1/2 a. How do I know that? Because 0.25 is half of 0.5, and they have to be related because of the units. So if this is acceleration, then the meaning of this slope must be half the acceleration. So let's take that and write a generalized equation. Oh, it's hard for you to see. Okay, we'll just do black. Okay, the generalized equation for this one is going to be that x is equal to 1/2 a t squared, because, right, this 1/2, or this 0.25 is half the acceleration. And the generalized equation here has got to be, right, just v is equal to a t. And there you have it. So this should, I think, help you answer the last couple of questions in the lab. So best of luck finishing up the lab. Thank you very much, and hope this helps.